So, hi, I'm André. I'm from Universidade Federal de Pelotas in Brazil. And this is joint work with my colleagues Jonathas, Samuel, Gerson, and Rodrigo. So, transactional memory is an abstraction for concurrent programming in which accesses to shared memory are performed as transactions similar to database transactions. And STM Haskell is a Haskell extension for transactional memory. So in STM Haskell, transactions are encapsulated in a monad, the STM monad. And inside of transactions, what you can do is only access transactional variables. So conflict detection is done in a fine-grained level, at the level of reads and writes to TVARs. And of course, it's impossible to access external resources inside of transactions because they have type IO. So what I'm presenting in this talk is Open Transactional Actions, which is a STM Haskell extension to access external resources inside of transactions. So what we want to do is to interact the STM, provide interaction between the STM world and the IO world. So inside of Open Transactional Actions, the programmer can execute IO and can also register commit and abort handlers to explain what to do with the resource once the transaction commits or aborts. So we believe that this could be used to implement useful libraries, for example, to access system resources, for example, file handling, and also to do transactional boosting, which is creating composable transactional versions from existing fast concurrent data structures. So let me talk a little bit about the problem that we want to address. So I'm going to talk about an example, which is implementing a transactional set using transactional memory. This is an example that I'm going to present later. So usually you could implement this using an ordered linked list, but the problem is that implementing linked lists using STM is problematic because especially when there is high contention, because when you transverse the list, you have to read many different addresses, and this might generate many false conflicts between transactions. But on the other hand, we know that in Haskell, we can implement a fast concurrent linked list using compare and swap. So what if we wanted to access a fast concurrent linked list inside of a transaction? We could think of using unsafe IO to STM, which transforms an IO action into an STM action, which is very dangerous. But this is not enough because these accesses to the linked list must be composable and also abortable. So looking at the related work, there's been some work on accessing resources from inside of transactions in transactional memory. And in these works, external resources are accessed as a black box, and because of that, conflict detection must be provided at the level of function calls. So the programmers must implement a semantic layer on top of the resource to guarantee that only commutative operations are executed concurrently. And also resources must provide or allow the implementation of inverses, so when the transaction aborts. So this is the kind of access to resources that we want to provide in STM Haskell using Open Transactional Actions. So before talking about our work, just a quick recap on STM Haskell. So it's a Haskell extension for transactional memory, and transactions are encapsulated in a monad, the STM monad, and inside of the STM monad, basically what you can do is read and write into transactional variables, TVARs, and transactions are composable using the monadic constructs and also some other constructs from STM Haskell. So this is the interface for STM Haskell. We have the TVAR, and we can write and read to tvars using write tvar and read tvar. Also, there is the construct retry that aborts a transaction and only starts it again once one of the variables that the transaction has read is modified. Also, there is the or else construct that is used for composition. It takes as arguments two transactions and it executes the first one. If the first one retries, then it executes the second one. If the second one retries, then the whole transaction is executed again. And all these constructs have type STM, and we can only execute an STM using atomically that takes an STM and transforms it into an IO action. So now open transactional actions are computations that may be executed by transactions in order to interact with the outside world. So open transactional actions are encapsulated in a new monad, the OT monad, and inside of OTAs we can execute IO. And open transactional actions should also explain what to do with resources that we are accessing if the transaction aborts or commits. So this is the interface for open transactional actions. We have this new monad, the OT monad. We can execute in the OT monad IO using lift IO. And we can also register commits and abort handlers using onCommit and onAbort. The onAbort actions registered are executed in a reverse order from the newer ones to the older ones. And also programmers sometimes might need to abort a transaction. So we have an abort construct. For example, when we can't get a lock for a resource, we probably have to abort the transaction, so we can use abort. And an open transactional action can be executed inside of a transaction using run OT, that takes an OT action and transforms it into an STM action. One important thing is that once a transaction starts executing an OT action with run OT, this transaction cannot be aborted. We guarantee that this OT action will be executed until the end. So the proper onCommit and onAbort will always be registered. So these primitives have a special relationship with retry and or else. When a transaction retries, the onAbort actions are executed. When a branch of or else retries, only the onAbort actions registered in that branch of the or else are executed. And if an abort is called inside of a branch of or else, the whole transaction is aborted. That's why it is different than retry. Also about exceptions, if an exception is raised and not caught, then the onAbort actions are executed. If an exception is raised inside of an onCommit action, the transaction still commits, but the exception leaks outside atomically. So if we suppose that this exception is an error, and we already started executing the onCommit actions, we don't know exactly where this error occurred, so we cannot undo these changes. So the idea is that we still commit the transaction, but we raise an exception to say that something went wrong. And also, it's not possible to execute transactions inside of OT actions. If you try to do that, the runtime system raises an exception. So I want to show some examples of the use of open transactional actions. So the first one is doing file access inside of transactions. The main idea is to use OT actions to acquire operating system level file locks. So file locks are read and write locks that allow multiple readers and a single writer. and file locks are not reentrant. So they must be acquired when opening the file and also released when closing the file. So this is the interface for our simple file access library. We can open a file using an I/O mode, and this returns a file handler, and we can read lines and write lines using the file handler. So this is the example of the code for opening a file. So opening a file in read mode. So this is an open transactional action, so we execute it using run OT. The first thing we do is to try to open the file. If we try to open a file that in read mode and the right lock for that file is already acquired, it raises an exception. So we use this try open file to try to open the file a number of times before giving up. If we can't open the file, then we abort the transaction. Otherwise, we try to acquire the read lock for the file. If we manage to acquire the lock, then we register on abort and on commit actions to unlock the file and close the handler. If we cannot acquire the lock, then we abort the transaction. Opening the file in read-write mode is very similar. The only difference is the type of lock that we try to acquire. Instead of acquiring a read lock, we acquire a write lock. So to write a line, it's also an OT action, so we use run OT to execute it. So what we do is we record the current position of the handler, and then we read the current string in that position. After that, we go back to the previous position and write the new string into the file. If the old string is shorter than the new string, it means that we were close to the end of the file. So then in case of abort, we write the old string back, and then we truncate the file to its original size. Otherwise, on abort, just has to put the handler back in its old position and write the old string back into the file. So read line is similar and is simpler because no modifications to the file are made. We only have to record the handler's position before reading a line, so we can put the handler back in that position if the transaction aborts or retries. So we have more examples. The other 3 examples I'm going to present are related to transactional boosting. So transactional boosting is a methodology to access a large class of linearizable objects from inside transactions. With transactional boosting, the base object is treated as a black box and is implemented without any notion of transactions. And transactional boosting adds a transactional semantics layer into the base object. So with transactional boosting, only commutative operations should allow to occur concurrently, and blocking mechanisms should be used to prevent non-commutative operations to run. So locks are acquired eagerly and released at commit time, and the operations that will be accessed by transactions, of course, must provide inverses for the case that the transaction aborts. So the first example is a very simple example that is taken from the original transactional boosting paper, which is a unique ID generator. So a unique ID generator is a shared counter that is incremented every time a transaction asks for a new ID. This is very problematic to implement using transactional memory because transactions are competing for the shared counter, so we might get many read and write conflicts. So if we think about this problem, different calls to the ID generator are commutative as long as they always return different IDs. If we abort a transaction, ideally, we should return the ID, the generated ID to the pool of IDs. But in practice, IDs are disposable as long as every call to the ID generator generates a different ID. So this is how we implement this using Open Transactional Actions. So the ID generator is an IOREF, and we use this function, getID cast, that uses compare and swap to increment the ID generator. This has type IO, and we can access this inside of a transaction by using run OT and lift IO to execute the getID compare and swap. So the second example is more interesting, is the implementation of a set data structure. So a set data structure is a collection of unique items, and it has functions for adding, removing, and searching for items. So these functions commute as long as they are accessing different items in the set. The inverse of an add is delete, and vice versa. And a call to contains is disposable if the transaction aborts. So to implement a transactional boosting version of this data structure to be executed inside of transactions, we use two fast concurrent lock-free data structures implemented in Haskell. One is a hash table taken from Medeiros, and another is a linked list taken from Sussman. So the hash table is used to implement abstract locking. So the hash table associates items in the set to locks. So if a transaction needs to operate on an item, it must acquire the lock for this item. And the items that are in the set are held in the fast concurrent linked list. So the set is represented by this abstract lock that basically is the hash table, and also the linked list where the items are maintained. The keys in the set are maintained. So this is the code for adding an item into the set. So it's also an open transactional action. So we use run OT to execute it. So the first thing we do is to try to acquire the lock for the key that we want to add into the set. This lock primitive, what it does is it finds the respective lock for this key. So then if we manage to lock this key, then we register a non-commit action to unlock it during commit time. And after that, we check if the key is already in the linked list. If it is not found, there is nothing we can do. We cannot add this item. So then on abort, we just have to unlock the lock for this key, and we return false. If the item is not already in the linked list, then we add the item into the linked list, and then on abort, we have to undo this. We have to delete the key from the list, and also the lock for this key. If we cannot lock the key, then we just abort the transaction. So the delete and contains function work in a similar way. So they must acquire the abstract lock for the respective item before accessing the internal linked list. If delete aborts, we must put the item back into the linked list. And if contain aborts, there is nothing to do besides liberating the lock for the key. Also, in some experiments, this linked list that we used in the set performed an order of magnitude faster, usually an order of magnitude faster than a linked list implemented in pure STM Haskell. So we wanted to access this linked list inside of STM Haskell. To do that, we needed inverses for the operations. So we modified the linked list. So instead of holding values of type A, it holds IO refs of maybe A. So with this, we can implement logical deletion of items. So we just have to write nothing into the positions. And then we can use the IRF as well to put the item back in that position if the transaction aborts. And to access the linked list, we use fair read-write locks that allow multiple readers and a single writer. So writes and reads cannot occur concurrently. And accesses that change the list are serialized. So we expect this scheme will work best for when there is high contention. So we performed some experiments with these transactional boosting examples. We used the server with 4 AMD Optron processors. It has 32 physical cores and 64 processing units. And we used a version of GHC that was modified to support Open Transactional Actions. So the details of these modifications that we did are in the paper. And each experiment was executed 30 times. So the first experiment uses the ID generator. We have 3 versions of the program. One that only uses compare and swap and no transactional memory. The second one is the transactional boosted version that I presented before. And the third one is one using pure STM Haskell that the ID generator is represented as a TVAR. So we do 1 million calls to get ID, and the calls are divided by the threads available. So these are the results. As expected, when we increase the number of threads, pure STM Haskell performs very poorly. And one interesting thing that happened here is that Open Transactional Actions perform better than the program using only compare and swap. But if we look at the numbers, that there is no significant difference between the times for these 2 programs. So the second experiment is with the set. We compared the set implemented using Open Transactional Actions with a set implemented as an ordered linked list of TVARs. So in the experiments, the initial set has 2,000 elements, and we execute 5,000 operations divided by the threads available. The initial set and operations are fixed and loaded from files. And in the Open Transactional version, Open Transactional Actions version of the set, the hash table of logs has an initial size of 2,000, which is the same size of the initial set. So this is the experiment with 70% of reads and 30% of writes with two threads. The transactional boosted version is 5 times almost faster than pure STM Haskell, and this increases up to 64 threads when the transactional boosting version is almost 15 times faster than STM Haskell. In the right dominant scenario, also with two threads, the transactional boosted version is 5 times faster than STM Haskell, and with 64 threads is more than 20 times faster. Also, the last experiment is using the linked list. So we compare 3 versions of the linked list. One is the linked list with no transactional memory. The other one is the transactional boosted version. And the other one is the using pure STM Haskell that was taken from the same paper that we took the concurrent linked list. So the experiment is the same as the one with the sets. The initial list has 2,000 elements, and we execute 5,000 operations. So in this experiment, with the with 7% reads in operation, then 30% writes, Open Transactional Actions perform better than STM Haskell up to 8 threads. After that, there is too much serialization happening. Remember that with this linked list using transactional boosting, all the operations that modify the list are serialized. So there is too much serialization, and STM Haskell can exploit better the parallelism. In the right dominant scenario is the other way around. In that case, it's known that it's better to serialize transactions. So in this case, the Open Transactional Actions version performs better in all cases. So I have presented Open Transactional Actions, which are a framework for accessing non-transactional resources from inside transactions. We believe that this could be used by expert programmers in 2 scenarios: to implement useful system libraries and also to access fast linearizable data structures from inside transactions. As future work, we would like to do an operational semantics for these primitives, also to think about higher level abstractions using Open Transactional Actions, implement more examples, and also port it to a newer version of GHC. This is a project that took some years to finalize, so we were stuck in this old version of GHC. So the source code for the GHC modified with Open Transactional Actions can be, and also all the code for the experiments can be downloaded from this link. So thank you.